Ja, just det. Jag brukar säga, eftersom det filmar så är det liksom...
Ja, just det.
So, most welcome today to the lunch seminar on the topic of exploring high energy universe with a balloon. Our speaker today is Mark Pearce from the Department of Physics and KTH Space Center. And as usual, this seminar is recorded, so if you have any questions, you're most welcome to ask questions, but it's easier if you take them in the end, and then you need to speak in this little microphone. So hands up if you have questions, and then I will go with the microphone to you. So thank you, Mark Pearce.
Okay,
please.
Thank you. So thank you all for coming to this lecture the week after Easter. It's nice to see you all here. So I'm going to talk about a project I've been involved in for the last, I guess it's 10 years or so. And we've been exploring the high energy universe. And when one thinks about exploring the universe, probably one thinks about using a satellite in orbit around the Earth, for example. But we have chosen to use a balloon. And this is not any normal balloon. So this is our balloon. And this is a balloon which is about double the size of Globen in the south of Stockholm. So it's about 200 meters in diameter. And it contains 1 million cubic meters of helium gas. And a balloon of this size is able to lift up our telescope here, which you can barely see, to an altitude of about 40 kilometers above the Earth's surface. So 40 kilometers is about 4 times higher than a standard jet plane will fly. And from this vantage point, 40 kilometers up, we can look outside of the Earth's atmosphere and we can register X-rays, so high energy radiation from various sources on the sky. So this is what I'm going to talk about during the next 45 minutes or so. So I normally like to start off by showing you my lab, right? Because I'm an experimentalist. I build hardware, telescopes, which we send up into space in various ways. And so this is my lab. This is the Milky Way. So this is the galaxy in which the solar system is placed. So the solar system is out here on the edges. This is a spiral galaxy. We believe there's a supermassive black hole here in the center. And the gas in the galaxy, which is primarily hydrogen, is swirling around. So it's kind of like water going down in a sink, in a plug hole. And this gas is swirling around, and the solar system is out here. So this is an enormous object. So it's rather like a giant pancake. So it's about 100,000 light years in diameter. So a light year is 10 to the power 16 meters, or this in standard notation. And it's only about 2,000 light years thick. So it's a very flat, very thin disk. And the solar system is about 30,000 light years from the center of the galaxy. So the Milky Way as a whole contains something like 300 billion stars, which we can observe, some of which we can observe with various telescopes and form a better understanding of the universe. So when one thinks about astronomy, one normally thinks about people that work in facilities like this. So this is a standard, so we say, astronomical observatory, where there is a telescope placed inside this dome here, and this telescope is sensitive to visible light. So normally when one thinks about astronomy, one thinks about looking through a tube with a couple of lenses or so and making images of objects through the visible light which they emit. So this is not the field of astronomy. So I wouldn't call myself an astronomer. Instead, I work with high-energy light, or X-ray radiation. And if we were to make, so here you see a picture of the night sky, and you can see here a sort of band across the sky. This is the plane of our galaxy. So in the previous picture, then this will be looking into the plane of the galaxy where most of the matter is. There's very little matter as one moves out of the galaxy, so out of the plane of the screen here. So this is the band. This band here is the plane of the galaxy, the disk. And we can also make similar pictures of the night sky, but rather than using visible light, we can use high-energy radiation, high-energy photons. And so this image comes from the Fermi Gamma Ray Space Telescope, which was launched more than 10 years ago, and which KTH built part of. And this is our sort of best picture we have of the high-energy gamma ray sky. So these photons have a much more energetic than visible light, but you see certain similarities with the picture I just showed. So for example, there's this band here so the intensity is, the colors give an idea of the intensity of the radiation. So yellow is very intense in gamma rays, red is a bit less so, and blue is the lowest level of intensity. And you can think about, we're looking out into the night sky and we're kind of opening up a sphere to form this kind of ellipse-like shape. So this is the plane of the galaxy, and the galaxy glows in gamma rays because charged cosmic rays, so high-energy protons primarily slam into the matter which is present in the disk of the galaxy, giving rise to the production of gamma rays. So this is this glow here. And you also see there are distinct kind of point sources here of gamma rays. So there are various objects on the sky which glow very, very strongly in gamma rays. And these objects are very interesting to observe. And the reason why they give off gamma rays rather than, say, visible light is because the temperatures in these objects is extremely high. And so you think about if you heat up a piece of metal in a fire and take it out, it glows red. It gives off mostly infrared radiation. You can put your hands close to it and you can feel the heat emanating off the metal. So the temperatures at play in these objects are well above 1 million degrees Celsius. And in that case, it's not infrared radiation which is given off, it's X-ray radiation. And then what you don't see here is the transient nature of the sky. So this is just like a snapshot of how the sky looks at a particular time. But if we were to have a video, we would see that a lot of these objects are very dynamical, that they change in intensity, and various sources will sort of appear and then disappear. And about once per day, we will see an enormous flash of gamma rays on the sky, a so-called gamma ray burst, where processes occur such that the same amount of energy that the sun emits during its entire lifetime is emitted in about 10, 20 seconds or so. And it manifests itself as this high-energy gamma radiation. And these objects are extremely interesting to study. But it's not those I'm going to talk about today. So instead, I'm going to show this picture. So this is our sun, taken with the SOHO satellite. And the two objects I'm going to talk about today, which are very important in the high-energy universe, are neutron stars and black holes. And both of these objects arise when a star dies. So let's assume that this is any old star in our galaxy. So let's pretend it's not the sun for now. So after some billions of years, this star will die. It will stop shining. So the reason why we see stars is because they emit radiation in the visible part of the spectrum, and we can then look at them through telescopes and so on, or even see them with the naked eye. And this visible radiation occurs due to the presence of so-called fusion reactions, so nuclear processes which occur in the center of the star. So what's powering a star are these fusion reactions. And so, for example, what you can have is, so we have to know a little bit about subatomic physics here, but we can have objects like deuterium. So this is a bound state between a neutron and a proton. And we can have tritium, which is two neutrons and a proton which are bound together. So these are both so-called isotopes of hydrogen. So hydrogen, or ionized hydrogen, is just a proton. So hydrogen is a proton plus an electron. If you ionize it, you remove the electron. So these are both isotopes, heavier versions of hydrogen. And because of the enormous pressures which exist in the center of stars due to the enormous mass which is pushing inwards, you can force these objects here, these atoms, to fuse together, to merge together. You can overcome the electrical repulsion due to the protons here. Each of these protons has a positive electric charge, and so they're quite difficult to push together. They repel each other a little bit like when you try and bring two magnets close to each other. But the forces are so great that you can fuse these two atoms together, these two nuclei together. And if you do this, you release energy. And the reason why you release energy is because when you fuse these two objects together, you produce helium, so helium gas, the same helium that we use to fill our balloon with, which consists of two protons and two neutrons, and you release a neutron here. And if you add up the mass of the neutron and the helium here, it is lower than the mass of the two constituent parts here. And this difference in mass, through Einstein's famous equation E equals mc squared, then causes a release of energy. You'll convert the mass into energy. And it's this energy then which eventually gives rise to the fantastic optical images, which we see here, for example, which gives rise to the visible light. So this is all well and good, and as long as the situation is stable, then the star will continue to shine, and for example, in the case of our sun, it's very important, of course, because it keeps the Earth warm, for example. But eventually, the situation will change, and what keeps the star stable is that you have two forces which balance each other. So you have in the center of the star, where you can fuse together these, for example, deuterium and tritium. These fusion reactions happen in the center of the star and in the core of the star, and these give rise to an outward going force, okay, which acts outwards towards the surface of the star, and this is primarily radiation. So it's the radiation which is released during these fusion processes. And of course, if this force was not balanced, then the star would simply blow itself apart. So there has to be something to balance this, and the balancing force is gravity. So it's the mass, all this enormous amount of material which is pushing inwards and is causing the core to compress and this system to remain stable. And so as long as you have these two forces which are in balance, then the star is stable and everything's fine. But eventually what will happen is that the fusion reactions will stop, because you fuse heavier and heavier elements in the surface, in the center of the star, and eventually you reach iron. And it's not possible to fuse iron atoms together in the center of the star, because it requires simply too much force, too much energy, and that energy cannot be produced by the amount of mass in the star. It cannot be produced by the gravitational force acting inwards. So as soon as you start to produce iron, then these fusion reactions eventually will stop. And of course, then you have a problem, because when they stop, then there's nothing to balance this inward acting force due to gravity. And at this point, the star collapses and forms what we call a supernova explosion. So it's an enormous explosion which rips the star apart. So the inner layers of the star fall towards the center, and then this free fall takes some seconds. It reaches the center of the star, the core, and the core is a solid mass which cannot be further compressed, and the whole thing just rebounds, and the shock wave travels outwards and blows the star apart, producing this fantastic supernova explosion. So as the matter falls in then, the core of the star is compressed slightly, and then eventually it just seizes up and stops, and then it rebounds. And during this process, then different things can happen depending on the mass of the star, depending on how much matter is present in the star, and which then falls in towards the center. So there are three different scenarios, two of which have rather spectacular outcomes, of one of which isn't so interesting, so we won't talk about it so much. So the three outcomes here depend on the size of the core of the star. And so if the core of the star is about the same as the mass of our sun, then, so this is actually the case for our sun, then there's simply not much will happen. The core will simply be formed, the outer layers of the star will be blown away, and one forms what's called a white dwarf star. And this white dwarf star will simply cool off over billions of years, and eventually it will even become so cool that it will simply stop radiating visible light. We will not be able to see it. And after that time, it becomes known as a black dwarf star. So this is not particularly interesting, it's just a slow cooling down. So what's more interesting is when the core of the star is more massive. So when the core is somewhere between 4 to 8 times the mass of the sun, then there's enough infalling matter that you can compress the core and interesting things start to happen. So in this scenario, sort of mid-mass scenario, you form what's called a neutron star, and I'll talk more about this in a moment. So it's a very peculiar object which we've studied with our telescope. And if the core is very heavy, so more than about 8 solar masses, then you can actually produce a black hole. So a black hole is an object where you can compress the material so much and the material is so dense that the gravitational field is so strong that nothing can escape from the vicinity of the black hole, not even light. And so it looks like just a void on the sky, since no light can escape from it. So in order to understand what this neutron star is and how it's produced, we need to actually turn back. So we're starting off by looking at some of the largest objects in the universe. We're looking at the galaxy and processes which are occurring inside the galaxy. But to understand what's happening inside this neutron star, we need to understand about particle physics and subatomic physics and what happens at the absolute smallest scales in nature. And we know a lot about how nature behaves at very small scales through, for example, experiments that we can do at places like CERN, where they have this enormous accelerator, which is 27 kilometers in circumference, where you can collide together protons at very high energies, producing new particles, so you can understand what the basic building blocks of matter are. And our model of the subatomic world is actually quite simple. We can summarize it on one slide here. No, okay. Inte bättre. Får stänga av det kanske. No, okay. Technical issue. All right, so our understanding of the basic constituents of matter can be summarized on this one slide. So we can go all the way from objects which have a size of some centimeters, let's say a block of metal, which you can hold in your hand. Let's say this is a block of copper, which I can hold in my hand. So it's a macroscopic, a large object. And our understanding of the laws of subatomic physics tell us that we can understand how the structure of this copper is built up, all the way down to distance scales of about 10 to the minus 15 meters. So it's an enormous range of distances here. So we're going from sort of, of order 100th of a meter down to this 10 to the minus 15 meters. And as you probably know, as we zoom in closer and closer, then this block of copper, we would find out, consists of a regular lattice of atoms, which we choose to depict here as kind of balls. It's not really correct, but it gives you an idea of how each of these balls is as an atom. And then as we zoom in further, then we know that these atoms, these aren't really balls. So there's a nucleus, which is surrounded by electrons. And again, it's not really the case that electrons orbit around the nucleus like planets orbiting around the sun, but it gives you a kind of a cartoon. And then these electrons here we think are point-like. We have not managed to discern any structure for the electron. It seems to be a point-like particle with no discernible spatial extent. Whereas if we look in the nucleus, we see that the nucleus consists of protons and neutrons. And we'll talk more about these in a moment. And then finally, at these particle physics experiments, they've managed to show that these protons and neutrons actually have an inner structure consisting of 3 so-called quarks. And these quarks are interesting for those of you that are studying physics because they carry non-integer electrical charge, which you're told in your, at least early lectures, this should not be possible, right? Because charge should always be quantized in terms of the charge on the electron. But it turns out that these quarks contain non-integer electric charge, but they must always be combined in such a way that the overall sort of final product, the proton or neutron, has an integer charge, either 0 charge or 1 plus 1 in your units of the electron charge. So then we can use our understanding of the subatomic world to try and figure out what happens when the core of the star is compressed. And so what happens is that the core of the star consists of exactly the same atoms that we can experience on the Earth. So you have atoms which consist of protons and neutrons here forming a nucleus, which are somehow associated, or is shown here, somehow electrons orbiting around this nucleus. And when the star collapses, of course, you're compressing this material down, so it occupies a smaller amount of space than it would do if it was just left alone, so to say. And what happens is the forces are so enormous that you can actually force the protons and the electrons to coalesce, to interact with one another and to form new objects. And this is controlled by the so-called weak interaction in particle physics. And the process which happens is quite simple. So a proton and an electron coalesce, they form they join together, if you like, forming a neutron and what's called an electron neutrino. More on this in a moment. What's interesting, though, you see here is basically what you're doing is you're converting all of the protons and the electrons in the atoms into neutrons. And this is where the name neutron star comes from, because you end up with starting off with a star which consists of protons, electrons, and neutrons, and then through this gravitational force, you end up with a star which comprises mostly of neutrons. So it's a very weird object, and not like anything that we can manage to create on the Earth, and this is why it's interesting to study. I say you also produce a prolific number of these electron neutrinos, about 10 to the power 58. And this is one of these numbers which we kind of throw around, but it's very hard to visualize just how big a number this is. So 10 to 58 of these electron neutrinos are produced. And these neutrinos are extremely difficult to detect. They interact very, very rarely with material. So of the fraction of these which will reach the Earth, the majority of them will simply pass through the Earth without us noticing them. They're extremely, they have a very, very weak, a very, very small cross-section for interactions, a very, very small probability to interact. So after the star has collapsed then, what we're left over with is a very strange object. So it's this neutron star. And the neutron star, it turns out, is about 15 kilometers in diameter. So it's the size of a small town. And it's like a giant atomic nucleus where this object contains about 10 to the power 57. So again, a huge number, which is very difficult to kind of visualize. So it's an enormous atomic nucleus with about 10 to the 57 neutrons and some unconverted protons and electrons. But it's primarily neutrons. So it's a very strange object. Like I say, unlike anything that we can produce on the Earth. And because it's so dense, it has very strange properties. And so, for example, this neutron star, which is only 15 kilometers in diameter, it weighs about the same as our sun, which has a diameter of about 1.4 million kilometers. So the sun is an enormous object, right? And it has this rather large mass. But this neutron star, which is very small, which you can kind of visualize the distance scale, 15 kilometers, you can, maybe if you're fit enough, you can probably even run 15 kilometers. You can't run 1.4 million kilometers. You can, the distance scale you can envisage. But this object is so dense that it weighs about the same as the sun. So it's very, very interesting. And because of this enormous density, it has some particularly strange properties. So one could think about doing an experiment to investigate this object. So we happen to have an astronaut at KTH, as you probably know, Christer Fuglesang, and I could sort of persuade him to go and visit one of these neutron stars. This will be quite difficult because the neutron star which we study is 6,500 light years from the Earth. So this means that if we could send Christer off at the speed of light, which we don't know how to do, but if we could, it will still take him 6,500 years to reach the star. Then he has to do his experiment and come home. So it's not something we could do for real. Well, let's just play with the idea that we could send Christer there, and he could stand on the surface of the neutron star. And, we don't have very much money to do research these days, so all I can afford is to give him a teaspoon, which I probably would steal from IKEA or something. So I send him to this neutron star with a teaspoon in his hand, and I ask him to do an experiment, and the experiment is, please dig out a teaspoon worth of material from the surface of the neutron star and bring it back to the Earth so that we can study it. So he does this, and what do we find when he comes home? Well, we would find that this teaspoon of neutron star matter weighs about the same as 1 cubic kilometer of rock. That would say it's about 1 billion tons. So it's enormously dense material. And the density is, I say, far beyond any of the sort of kind of density which we can experience on the Earth. And so it's very interesting to understand better how this material is produced and what properties it has. So it turns out Christer would have quite some problems if he went to this object, because as he came in, as he was kind of thrown out of his spaceship and had to traverse the last meter down to the surface, because of the intense gravitational field which this very dense object produces, he would fall to the surface in about 1 microsecond, so 1 millionth of a second. And assume he starts with no velocity, with 0 speed, only 1 meter above the surface, he would hit the surface of the neutron star at about 7 million kilometers per second. So he wouldn't be very happy, I don't think. And if that's not enough, the surface gravity is about 100,000 million times that on the Earth. So he would be immediately crushed into a pancake. And then finally he would burn up because the surface of the neutron star is about 1 million degrees Celsius, which is why it radiates in X-ray. So it's an extremely hostile environment and a very interesting place to understand, and to understand physical processes which we cannot create on the Earth. And this is why I think it's interesting to study these objects. So when we see neutron stars on the sky, we normally see them like this. So this is the Crab Nebula. This is what I've been spending my time studying over the last few years. So this is actually the remnant or the aftermath of a supernova explosion, which occurred in the year 1054 and was actually registered in historical notes by Chinese and Asian astronomers, and then was rediscovered by a British astronomer in 1731. And this object is about 6,500 light years from the sky, light years from the Earth, and the size is difficult to discern, but it's about 0.1 degree in angular extent here. So this is, like I say, I'm not an astronomer, so I'm not very good at these things, but I think it's if you hold your finger up like this, away from your face, the angle which your end of your finger subtends on the sky is about 0.1 degree, thereabouts. So that's roughly how big it is on the sky. And this is an image taken by a series of different telescopes superimposed. This is not from one telescope. So the reddish color here comes from a radio telescope, where you're looking at rather long wavelength electromagnetic radiation, rather low energy processes. The sort of yellow-greenish here is from optical measurements from the Hubble Space Telescope, and then the kind of bluish glow here in the center is from an X-ray telescope. And so as you move in from the outside to the inside, then the energy of the radiation increases because the engine which powers this nebula is a rotating neutron star at the center here, which you cannot see directly. It's too small. So these pulsars are how we often see neutron stars. And a pulsar is nothing more than a rotating neutron star. So in the sense, this is a kind of cartoon. So here's the neutron star. And it turns out that when a star collapses, usually stars are rotating. And when it collapses, then you go from something very large, which is rotating rather slowly. And it's the same thing when you see someone doing ice skating. They often, if they're spinning, they hold out their arms and they bring their arms in closer to their body and they spin faster and faster because they have to conserve angular momentum. And it's the same thing for a star. So when the star collapses, then the neutron star is spinning much faster than the original star. And this neutron star, in this case, has a rotational period of about 33 milliseconds. So this object, then, which is 15 kilometers in diameter and weighs about the same as the sun, is rotating about 33 times per second. Right. So it's a very peculiar object from that point of view, a very heavy object which is rotating very, very, very fast. And just like for the Earth, the object has a magnetic field, and the magnetic axis is not aligned with the rotational axis. And those of you that do orienteering will know about this, when you have to offset your compass to take into account the Earth's, the declination in the Earth's magnetic field. So the neutron star is rotating around the rotational axis here, and then the magnetic axis is like this. And the magnetic field lines here, these act as a kind of a funnel which kind of dictate how high energy radiation is emitted from the neutron star. And so the particles find it easier to escape from the neutron star along the magnetic axis here. And so you have this kind of emission. In this case, radio emission is shown, but other wavelengths are also possible, for example, X-rays. And it's funneled out along the poles of the neutron star here. So you have this object then which is rotating, and then there's this kind of beam here which is spinning around on the sky. And so if you have the right angle to the neutron star, you will see this beam flying across your field of view. It will flash past your eyes, and it will look like the object is pulsing on the sky. And this is where the word pulsar comes from. So these things were first discovered in 1967 in the radio part of the electromagnetic spectrum, because it was easiest to build radio telescopes. And when it was first discovered, it was noted down as LGM1 in the notebook of the research student Jocelyn Bell-Bonnell, who discovered these objects. And LGM1, this was a kind of, I guess because she's English, she thought it was funny, and it stood for Little Green Men. Because, of course, when they first discovered this, there was this regular pulsation on the sky, and it wasn't really clear what it was. And so one of the things they had to exclude, of course, that it was some kind of signal from some extraterrestrial life or something. And this was rather straightforward to do. So this then shows how such a thing, again, schematically would look on the sky. And here you see this kind of lighthouse effect. So here's the neutron star rotating, and here are the beams of radiation. These white objects are the beams, and you see now and again they will spin past your field of view and you see this flash on the sky. So they're rather easy. Once you point your telescope in the right direction, these things are quite easy to see. So these objects have certainly been studied a lot in all different wavelengths, including X-rays, which I work in. And we have these fantastic images from telescopes like Fermi. But what makes our approach different is that we measure a particular property of the radiation which is not normally measured. And so normally when one does astronomy, one is measuring photons, electromagnetic radiation, which is released from these objects, and which then eventually enters the solar system and can be detected by instruments orbiting around the Earth. And this electromagnetic radiation can be characterized normally in three ways. So you can figure out where on the sky the radiation has come from, thereby building up a map like this. You can figure out if there's any time dependence of the radiation. You know, is it constant? Does it vary with time? And then you build so-called light curves, where you see how the intensity of the radiation changes as a function of time. And then finally, you can build instruments which measure the energy of the radiation. And thereby you can make energy spectra. But because this radiation is an electromagnetic wave, there's an additional piece of information, and this is the polarization. And this is what we measure, which is very unusual and sets our measurements apart from everyone else's. And so the polarization is simply, if you think about the radiation being an electromagnetic wave, it's simply the plane in which the wave is oscillating, like this. So a wave with vertical polarization will oscillate like this, and a wave with horizontal polarization will oscillate like this. And normally, most light sources are not polarized. So standard light bulbs, they give off completely unpolarized light. But it turns out that for these high-energy sources, often they give off polarized radiation. And so it's rather interesting to measure this. And if you don't measure it, somehow you're missing out on the information carried by these photons from the source to the detector, to your instrument. So it's definitely worth measuring. And we have focused in on two objects. So one is the Crab, this nebula, this expanding shell of gas, which comes from a collapse of a star in the center here, which is then flung off its outer layers, forming this nebula, which is expanding, leaving behind a neutron star in the center. And in this case, we're particularly interested in understanding what happens when electrons in very close to the pulsar here in the center, these electrons are charged, they have a negative electric charge, and when they encounter a magnetic field line, they will gyrate around the field line like this. And this gyration gives rise to what's called synchrotron radiation. It gives rise to the emission of X-rays, and these X-rays will be polarized. And it turns out if you can measure the polarization of these X-rays, you can say something about the geometry of the magnetic field close to the pulsar. And this is something which you cannot get from standard observing techniques. So it gives you a new window on these sources. The other source which we've studied is a source called Cygnus X1, and this is a so-called black hole binary. So this is a black hole here, and it's in a binary pair with a supergiant star. So it's in very close proximity to a supergiant star, and because this is such a heavy object, this star, the outer layers of this star, are kind of sucked off and form this disk here, which rotates around the central black hole here, kind of like water going around a plug hole. And it forms a so-called accretion disk. So it's like a flat disk of relativistic matter rotating around like this. And what happens here is polarization is interesting because radiation can scatter off this disk. It can, just like photons or light can scatter off the surface of a lake or something, surface of a pond, and the scattering, then the scattered radiation can be polarized. And if you can measure the polarization, you can say something about the geometry of this object, which again, you cannot see with standard observing techniques. So normally when one thinks about how do we measure polarization? How do we measure this polarized radiation? One can think about sunglasses. So if you have a pair of Polaroid sunglasses, you'll be familiar with polarization, even if you don't know it. So Polaroid sunglasses contain lenses here which have polarization filters built in, and these are particularly good at removing the glare, for example, of water. So if you do a lot of fishing or spend a lot of time on your boat or something, you probably have a pair of these glasses. And so when the sunlight which is unpolarized, scatters or reflects off the surface of the water, the act of reflection polarizes the light. So the incoming light is unpolarized, but the outgoing light will be polarized, and the polarization direction is parallel to the surface of the water. So if you then have a pair of sunglasses where you have filters here which can block this component of polarization, you will remove the glare. And this is exactly how the sunglasses work. So this is without sunglasses, and this is with sunglasses. You see that most of the glare here has been removed. So you cannot use this technique for X-rays, unfortunately, because it's not possible. Because of the wavelength of X-ray light is so short compared to visible light, it's not possible to build filters here with sufficiently short distance between those kind of filtering components. And so instead, you have to rely on a different technique, and this is what we've had to develop, an instrument which can measure the polarization of X-rays. And so we built a camera, and it's a very lousy camera. It only has 61 pixels. You know, we're used to millions of pixels nowadays. And what we do is we register how photons scatter, how they move from one pixel to another. And it turns out that this movement, this scattering, as the photon comes in, it scatters between pixels, and the scattering angle, it turns out, depends on polarization. So we have to do this outside of the Earth's atmosphere. So this shows how transparent the atmosphere is as a function of wavelength. And you see here that the Earth's atmosphere is very good at blocking high energy radiation from space. So we must do these experiments outside of the Earth's atmosphere. So we do this by releasing balloons from the Esrange Space Center up in northern Sweden, just outside of Kiruna. There's a large area from which one can release these research balloons. So what I'm going to do now is show a film for 5 minutes or so, if it works, which should hopefully give you an idea of how exciting it is to do this type of science, to build a telescope and then release it on a balloon. Let's see if we can get the technology to work here. So this film was, well, there it is, produced by SSC, which is Rimbolaget, who are responsible for running Esrange. So probably I won't show the entire film, but I'll show enough so you get some idea of how such a balloon launch works. So I'll stop it there. If you go onto YouTube, you can find you can find the full-length version, which includes footage taken from the balloon as it's flying at 40 kilometers. It's quite impressive. You can look down on the Earth from that hatch, and also you can see the end of the flight where the balloon is umpuned by remote control. There's an explosive cord on the balloon. The balloon umpens, and everything falls back to ground using a parachute. So this is the equipment then we built at KTH. Here is our telescope, and then it's inside this very large gondola, and yeah, all the various equipment which is needed to do these types of balloon flights. So I see I have to speed up a little bit here, but let me just say that 2016, then the flight was very successful. We flew for about 1 week, launching in the north of Sweden, and we flew on a line of roughly constant latitude, landing about a week later in northern Canada on Victoria Island, and the whole way we have contact with the balloon using radio link. So I say, what did we actually measure then? So very briefly, we made, this is a very complicated figure which comes from the journal publication, but what you see here is the blue line gives you the intensity of the radiation, which has this characteristic pulsing structure due to the rotation of the neutron star. And we make the very first measurements of the polarization of the emissions from the Crab. And what was perhaps a little bit unexpected was that the polarization value is rather high. So about 20 or so % of the photons were polarized in a certain direction, which is maybe a little bit unexpected due to the very sort of chaotic environment around the neutron star. And it probably tells us that these photons are arising from a magnetically ordered area, in other words, a region around the pulsar which is rather small. Let me just go on last couple of minutes, talk about Cygnus X1. So this is a binary system between a supergiant star, about 30 solar masses, which accretes matter onto about 15 solar mass black hole. And this object, this is an artist's impression. We don't really know how it looks. The best telescopes give us an image like this, right? So we just see it as a prick of light on the sky. But by measuring the polarization, we can understand the geometry in the vicinity of the black hole in a completely new way. And so in particular, the matter which lies very close to the black hole here is in a region where there's extremely strong gravitational fields. And Einstein's theory of general relativity dictates how the photons move around this black hole. So those of you that have seen the movie Interstellar have seen these fantastic images where they've ray-traced photons moving around a black hole, forming these very strange geometrical shapes. So it's worth seeing that movie if you haven't seen it. Incidentally, the ray tracing software was done by Kip Thorne, who won the Nobel Prize in Physics last year for the detection of gravitational waves. But what we managed to do, this is a very complicated slide, is that we can probe how the matter is distributed in the very close vicinities of the black hole. And this is a work which is currently in review in a journal. So I will finish up there with my last slide. So by developing this telescope at KTH and by developing a telescope which can measure electromagnetic radiation from the Crab and Cygnus X1, we look at these two high-energy sources on the sky in a new way. And, I mean, stratospheric ballooning is rather challenging. We had several failed attempts, but finally we managed to launch this balloon and make some nice measurements. And, of course, one of the advantages is that thanks to this parachute here, you get your equipment back to the ground, and so if you fail the first time, you can try again, which, of course, you can't do with satellite missions. And I'll just end up here by showing the team who are up in S-range together with myself. So here we have all the students, postdocs, and so on, engineers who have helped to make this mission a reality. And here are various sponsors and collaboration partners, Stockholm University and Hiroshima University in Japan, primarily. Okay, I'll end there. Thank you.
Thank you very much, Mark. Do you have any questions? Hands up. Yes.
We're speaking a lot about rotation, but what about the balloon? Doesn't it rotate? How can you direct it?
Yeah, it does. Right, that's a good question. So this is a very interesting sort of topic. So we developed a so-called attitude control system here together with a company in Linköping called DST Control. And the purpose of this system is to allows you to track, I mean, the crab, for example, moves on the sky like the sun. And we have to follow it with an accuracy of about 1/10 of a degree as it moves. And this we do with this attitude control system. So the balloon, as you say, the balloon is like a giant torsional pendulum where the gondola wants to move underneath. So we have a system here with motors which work against the cable connected to the balloon in order to null out these rotations. So we can sense in 3 dimensions the orientation of the gondola, and then we have correction signals we send up to motors to keep the gondola perfectly still under the balloon. So it's an active control system.
So, more questions? Yes?
You've mentioned that it's 6,500 light years away, right? But how do you make sure that you're measuring the right electromagnetic radiation? Because they're
yeah, right. Okay, well, for the case of the crab, it's rather straightforward because this pulsation pattern is very hard to mistake for something else. So in the case of the crab, we simply look for this pulsation and we make sure it has the correct period. For the case of Cygnus X1, for example, we can confirm that what we do actually do is we stare at the source and then we move off by a few degrees, then we come back and then we move off like this, and we check that the counting rate of photons increases as we move on and then it decreases as we move off, for example. So this allows you to check that you're looking in the right direction, or looking at the right object.
So, more questions? No? So I actually wondered, how common are these objects that are sending out polarized light in the universe?
Oh, they're very common. So this is, I mean, I would say this is a more or less unexplored area of astronomy and astrophysics. So people are now starting to propose missions where this will be studied routinely, but really it's taking the first steps now. So there are many sources which we believe give rise to polarized emissions. Due to, for example, objects have strong magnetic fields with synchrotron emission producing polarization, or objects where photons scatter off these accretion disks, for example.
So do the measures get interfered by multiple objects in the same
No,
position?
so our instrument's rather sort of basic. So we basically just image a chunk of the sky, which is about 2 degrees square. But we know what's there from other missions, so we can be sure that there's no interference. I mean, new missions will have much better imaging, where they can look at a much smaller area of the sky, so-called imaging polarimeters.
Okay, thank you. Well, thanks again, Mark.
Thank you.
If you have watched our lectures, you would know that we give this as a gift
thank you.
lectures. I hope you don't have it already.
No, I don't actually.
Oh,
that's very good.
Great.
Thank you very much.
Thank you, and thank you for listening. And our next lecture will also have a space theme, so to say, because now I just have to check the date. The 11th of April, Göran Marklund will talk about electrical field measures in space, or elektriska fältmätningar i rymden. It will be in Swedish. So please come back, and thank you again.
Thank you.